Have you ever looked at a problem and just thought, this simple straight line answer just doesn't feel right? That is exactly where nonlinear programming, or NLP, comes into play. In this explainer, we're going to break down what it is, and way more importantly, how you can actually use Excel's solver to tackle some seriously complex, real-world challenges. So this is the big question, right? In the real world, things almost never move in a straight line. You've got diminishing returns, you've got complex interactions. There are curves everywhere. So how in the world do you find the absolute best solution when things get messy? Well, that's precisely what nonlinear programming helps us figure out. To really get why NLP is so powerful, we first have to talk about why those simple, straight-line models, as useful as they are, sometimes just fall short. And this slide, well, it lays out the fundamental difference perfectly. Linear programming, or LP, is great for simple, proportional stuff. You put in one more hour, you get one more unit of output. It finds one single best answer. But NLP is built for reality. It handles all the curves, like economies of scale, or how that 10th cup of coffee doesn't help nearly as much as the first one. This means there isn't just one peak to find. There's a whole mountain range of possibilities out there. Okay, so with that difference crystal clear, let's get a little more formal and define what actually makes a problem nonlinear. At its core, NLP is just the way to optimize models that aren't straight lines. And as you can see right here, the moment your formulas involve things like multiplying two variables together, or using exponents, or even a function like square root, boom, you have officially left the linear world and you're now in the world of NLP. And hey, a quick but really important clarification. If you hear someone throw around the acronym NLP, you might be thinking of AI, chatbots. That's natural language processing. What we're talking about today, our NLP, is all about mathematical optimization. Same letters, totally different universes. Okay, now we're getting to what is, honestly, the single biggest challenge in NLP. It's this critical idea of understanding the difference between finding a peak and finding the peak. This mountain range analogy is just the perfect way to think about this. Imagine you're climbing in a really thick fog. You finally reach a summit and you stop. You think you've made it. Well, you're at a local optimum. It's the highest point you can see from where you are. But hidden in that fog, there could be a much, much taller mountain, the global optimum. For a business, that local peak might be a profitable strategy, sure, but that global peak, that's the most profitable one possible. And here's why this is such a huge deal. An NLP solver can actually get stuck on one of those smaller, local peaks. The starting values you plug into your model can literally determine which hill the solver decides to climb. This means your initial setup doesn't just matter a little bit, it can completely change your final answer. Okay, that's enough theory. Let's roll up our sleeves and get practical. How do we actually build and solve one of these models in a tool pretty much all of us have, Microsoft Excel? A well-organized spreadsheet is your best friend here, trust me. Start by color-coding your cells. It's such a simple habit, but it pays off big time. Green for your decision variables. Those are the numbers solver gets to change. Blue for your objective. That's the goal you're trying to max out or minimize. And yellow for your constraints, your limits. Then you write the formulas that tie it all together. And remember, the second you multiply two of those green cells together in a formula, you've just built an NLP model. Finally, you open up the solver tool and tell it how to solve your puzzle. Now, this next step, you absolutely cannot miss this. Inside that solver window, you have to change the solving method to GRG nonlinear. This stands for Generalized Reduced Gradient, which is a fancy way of saying it's the specific algorithm built to navigate the complex, curvy landscapes we've been talking about. So setting up the model, that's half the battle. The other half is all about mastering the settings to make sure you're not just getting an answer, but the best answer. When Solver's done, it's going to pop up with a message, and you need to know how to read it. Solver found a solution. That's great. That's what we want. But if you see something like Solver has converged, that means the improvements got so tiny that it just gave up. Now, that might be your best answer, or might be a hint that you need to go back and tweak the settings to make it search just a little bit harder. Knowing what these mean is absolutely crucial if you want to trust your results. So how do we hunt for that global optimum? How do we increase our odds of finding Mount Everest and not getting stuck on some smaller foothill? Well, lucky for us, Excel gives us an incredibly powerful feature for exactly this. It's called the multi-start option. Think of multi-start as sending out a bunch of different teams of climbers, all starting from different places on the mountain range, all trying to see who finds the highest peak. Population size is just how many teams you sent out. But here is the real pro tip. The one you have to remember, you must check the box that says require bounds on variables. Giving Solver a defined search area, like telling it a variable has to be between, say, 0 and 100, stops it from wasting time looking at impossible answers, like negative production numbers. It focuses the search where the real solution lives, and it makes the whole process so much more effective. So there you have it. We've gone from the theory of why problems get curvy all the way to the practical Excel tools you need to find that true highest peak. You now have this powerful framework for tackling problems where the complexity of the real world just can't be ignored. The only question left is, what problem are you going to solve first?